0. So that is minus 1 and open loop pulse. And that is 0, 0. Okay, so from here we can see how can we do it. So we can draw this one here. And that is the complex plane. So we have the open loop 0. So here is 1 here. So that is s equal to minus 1, corresponding to k equal to 0. And here we have a double pulse as a region here. So that is s equal to 0, corresponding to k equal to 0. That would be a good exercise for you to, from the beginning, to keep a good exercise is this. Write down the location of the particular, apparently particular point, for example, zeros and poles, and write down the corresponding value of the k at those particular points. Okay, so that will be the typical good exercise here. Okay, so now from here, then we can apply is we try to starting from the easy part. So that means we can determine the portion of the root loci on the real axis. Okay, and that one we know that is to the number to the left of a number of 0 and poles, right? So that should be here. You good? Okay. So that is a portion, and also it will be this portion, but that is unstable. We are not concerned. Now for this portion, we know that this is approaching to k. The k infinity. Sorry, at the 0 here, the k corresponding is infinity. So here is this one. Okay. So we know somehow the approaching to there, and there's another 0 at the infinity. So we suppose there's 2 branches. We expected 2 branches. Okay, the branches is starting from here, do some way, and then ending up like this. And now the next one we can determine is, say we know the root we're starting from here. So now we're going to determine the departure angle, right? The departure angles. For example, here we can place a little, a little test point here. Okay. So here I exaggerate. So this point is supposed to be very close to here because we're going to study the angle of departures here. If you like, you can proceed in your calculation directly and verify with my answers here. But here for the illustration, I do slowly. So for these departure angles, basically here is this. By definition, this is our phi departures. Okay, how to calculate this one? Stick with this. And we know that for this case, the angle s plus 1 and s squared equal to minus 1 over k. So that means the this one is minus 180 degrees plus L 360 degrees. Okay. So now for this case here, we have is this locally, and that is this one minus s2. And equal to minus 180 degrees plus L 360. Okay, so from here is this. So at the let me call the test point is S dot. Okay, the S dot is our test point, basically very close to there. And this equations is from this point, basically this point, the test point is very close to here. So this one. This angle is determined by simply is this one, right? So that vector equal to 0 degrees. I shouldn't use the red one because I here for my color notation, the red color is for locus. Okay, so that is 0 degrees, and then minus. This one, this meaning is the departure angle respect to this one, so that is 2 times of the departure angle, right? Minus 180 degrees and plus something there. So from here you can see the departure angle, if you keep playing, plus L times 360. So here we have 2 numbers will be equal to 90 degrees or minus 90 degrees quickly. Okay. So basically that angle basically here is locally is tangent to the imaginary axis, okay? And we know it must curve to the left because we know that eventually the curve will be going to here. Okay, so we can pretty much curve to the left. If you are so picky, asking why it's curved left, I can tell you why not you try one more test point. For example, you can try this test point here. Okay, and you can set this test point. For example, you can actually put, say, this one is minus 0.1, so we can set a test point equal to minus 0.1 plus certain j omega. Omega is unknown. You can use this particular point, apply the phase angle criteria, or apply whatever the method. You can verify that one. Basically, this point must be part of the root locus. This point must be to the left of the image axis. That is the sequence. You can, if you are really picky, you can do that way. But here, we can pretty much just do it, approximate roughly. Okay. So one branch will starting from here and go somewhere and coming back, and the other branch will go somewhere and coming back. And then we know one branch will be coming in to a certain point. This will be coming in here, and then come to that direction, go to the other directions, and this one basically goes to infinity there. Okay, so this point is what we categorize as the breaking point. Okay, so for the breaking point, again, we can exercise is this from that characteristic, from this characteristic equations s plus k, s plus 1 equal to 0, and no. K equal to s squared and s plus 1, okay? And then dk, ds equal to 0, so that means ds of s squared and s plus 1. So right now we apply the rule number 6 here. Okay, and finding the roots here, so basically this one is minus, okay, minus, sorry. So basically this one you can find easily, that should be s equal to 0 and minus 2. Okay, here I skip a few steps, but you should be able to find, to do the derivative of this expression. And then finding the roots there, so 2 roots, okay. And this one is our answers here, so that is at s minus 2 here. You good? Okay. So that is to complete this example here. And if you like to use MATLAB, the MATLAB basically the command is RLOCUS. Okay, this is a command, and how to use this command? Using our example here, basically you have to describe the open loop system. This is our open loop system. So describe the open loop system numerators equal to 1, 1. And denominators equal to 1, 0, 0. Then you can have the root locus. I believe you can say numerators, denominators, or if you like, you can have the system defined by the transfer functions of the new denominator, and then you can use the root locus system. I think either this way or either this way should work. Okay, so that is the MATLAB math here. Okay, that is this example. You can stop. Next.